Hear me? Awesome. Okay, so yeah, I'll be talking about how we at GoFood built a query semantics engine to help our users find food faster. So let's start. Let me start with a little bit about myself, but like as Usha already mentioned, I've been working as a data scientist for the past 3 years, but my background was in physics. And yeah, I've written a book called Applied Supervised Learning with Python. And oops. Yeah. And yeah, I'm currently working as a data scientist at GOJEK. So just a show of hands, how many of you have heard of GOJEK? Okay, it seems like most of you have, but let me give you a short introduction. So GOJEK is Indonesia's first and fastest growing unicorn. It has grown over 11,000% over the past 3 years. And now it's what we call a super app with over 20 services and operations in 4 countries. So a little bit about what we're going to be talking about today. First, I'll start by introducing the search context, why we need a query semantics engine and how it adds value. Then I'll talk about what is the previous workflow that we had and what is the proposed workflow. Then I'll go into a little bit into more detail about what are the steps inside the query semantics engine and how we built those components. Then after that, I'll talk about how we generated the Elasticsearch query that took into account all these components and what our results were. So yeah, first about the search context. So pretty much every application has a search bar of some kind. Some people use a search bar for filtering of sorts. For example, if you're searching for a specific word within a web page, or some people use a search bar for something like a discovery tool. Like if you're searching for something to eat, you want a biryani, but you don't know what kind of biryani you want, for example. So the way that we look at search, we divide it into two primary components. So the first one is around retrieving documents, retrieving all relevant documents. This step includes processing the query and extracting all meaning that we can get out of it. And the second one is around ranking. So this includes processing the query after processing the results after we've gotten the results, and this can include like filtering or personalized ranking, etc. So this is what our app in GoFood looks like. So GoFood is the food delivery platform inside Indonesia, inside GoJek, and we process like millions of orders per day. So we have two types of search. The first one is a text-based search, and the second one is a non-text-based search. So in text-based search, essentially what you do is you type in a text query, it returns results that match the text query. The second one is essentially we have category shortcuts and cuisines. So these are merchant lists, which can be like a list of merchants which are like 24 hours, or you can see, okay, you can't really see clearly on the screen, but we have new this week, promotions, near me, etc. So these are lists that can be personalized or non-personalized. So our focus for this talk is going to be around text search. Now let's talk about why we need a query semantics engine at all. So when we look at this set of results, I don't think it's very clear on this screen, but every single result on this page shows, has a restaurant which has the word burger in it when the search query was burger. So this makes sense if you're looking for a restaurant like Burger King. But what if you're looking for a restaurant like McDonald's or KFC, but because you just want to eat a burger? This is not a very optimal way of surfacing results. So this was what the problem that we wanted to solve. Our search only surfaced matches from native Elasticsearch functions. We had exact and partial matches, and at most fuzzy matches. And this is what we wanted to do to solve it. we wanted to add a component that could understand the query and understand the semantics and context from what the user was looking for from what they typed. So how does a query semantics engine actually add value? So if your search engine is able to understand what you're looking for, it would obviously reduce the amount of effort that you put in to actually search and find and order what you want. That means that you would probably be more satisfied with the service, with the app, which means that the overall user experience becomes better. And for us, that means there's a higher search to booking conversion. So what do we need to do to build the query semantics engine? How do we essentially understand the query that the user has typed? So we ask ourselves two primary questions to kind of figure out what are the next steps that we need to take. Let's look at what those questions are. So the first one, how do we identify the searcher's intent? How do we know that the query that the person typed in is referring to a dish, a restaurant, or a cuisine? So for example, if you're searching for coffee, how do I identify whether coffee is a dish? Is it the name of a restaurant, or is it a type of cuisine? So this is done by building an intent classifier. The next question is how we show additional relevant results without adhering to exact text matches. So for example, if you're searching for coffee, you would probably be okay with results that include cappuccino, espresso, latte, etc. So how do we surface those results, matches to those words as well as what the user searched for? So we do this by using a technique called query expansion. So now let's move on to what was the existing workflow and what we wanted it to look like. So in our existing workflow, we had an input query typed in by the user, which was then sent to ElasticSearch. And ElasticSearch effectively just returned a list of restaurants in which the name matched the search query. What we wanted was a piece in the middle before the query gets sent to Elasticsearch that can kind of derive the meaning from the query, something that can understand the query, figure out what the intent is, figure out what the other similar words are that we can also search for. So this query understanding bit that processes the raw text query is something what we called as a query semantics engine. So let's look at what were the components that we built for the query semantics engine. So first, we have the original text query, which is then sent to a spell corrector. So the spell corrector kind of ensures that whatever the search query the user typed maps onto an existing word in the corpus from our data. So if you typed coffee with, say, COFFE, that's not a word that actually exists in our corpus because that's probably not the name of a real dish.
Hello. Check. Hello.
Sorry? Okay, I'll just continue. So this is like COFFE is probably not a word that exists in the corpus. We wanted to make sure that whatever the search query the user typed existed in the corpus. So the next one was an intent classifier. We wanted to figure out what the search query that the user typed actually referred to. So if the person types coffee, are they referring to a dish, a burger, or a restaurant? So we did this by the next step was an intent classifier. So the last step that we had was a query expansion bit. So what the query expansion bit would do, so if you have typed in coffee, it would return the similar words that existed, like cappuccino, latte, espresso, etc. Then once we had the outputs from the intent classifier and the query expansion bit, we took these outputs and built an Elasticsearch query that incorporated them, and then we sent that query to Elasticsearch to return a list of all the relevant restaurants that were there. Now, how do we actually build these components, right? Let's start with spell correction, which is the first step. So we just had a simple frequency-based spell corrector, which took into account unigrams and bigrams that existed in the corpus. Let's look at an example. So if you type crispy with a K, it checks whether this word is there in the corpus or not. So it does find crispy with a K, but with a count of 1000. Then it checks if there is any other word with a certain edit distance threshold that is away from crispy, and it finds crispy with a C, which has a count of 10,000. That means it's more likely that the person actually typed crispy with a C wrong as crispy with a K, which is why we correct the query to crispy with a C, even though crispy with a K exists in our corpus. Now, you can imagine that there might be certain challenges with this, right? What if the person was actually looking for a restaurant called Crispy Krem, and they intentionally typed in crispy with a C? So one way that we can work around this is that even though this query is spell corrected, we make sure that we have a fuzzy match in our Elasticsearch query clause to make sure that it also matches with other words that are a certain edit distance away, like the user's original query. So we talked about how we spell corrected the query. Next, we'll talk about the intent classifier that we built. So we had 3 labels, as I mentioned before. We had dishes, restaurants, and cuisines. What we did was, like, in our corpus, we knew what were the list of restaurants, we knew what are the list of dishes, and we knew what are the list of cuisines that we have. So we just took all of these labels, all of these entities and the corresponding labels, and built a training data set using that. So we used the fast text algorithm to train an intent classifier. What fast text does, it's actually like a very popular text classification or a supervised text learning algorithm library that is used for text-based data. So this is what our training data look like. So on the left, we have the entities, and on the right, we have the corresponding labels, which we know because this is exactly the mapping that they have in our corpus. So how do we actually predict the intent? We use fasttext to give us an output probability of what each label can be. So when we have a search query coffee, so for the prediction label dish, we can say that the probability is 0.67%. The algorithm will predict the label restaurant with a probability of 13%, and it'll predict the probability of it being a cuisine with a probability of 20%. So these are the values that are eventually sent to Elasticsearch. These probability values that you see over here. So some of the challenges that we faced. When someone types in burger, are they referring to the dish burger, or are they referring to the restaurant Burger King? So this is a very common problem that we see, especially in Indonesia, because Burger King is a very popular restaurant there. And it effectively contains a word that refers to a dish as well. So in order to account for this, we use something called intent enrichment, where it was something as simple as just asking the user what they actually mean. So when someone types in burger, we ask them, do you mean burger as a dish? Or are you referring to burger as a part of a restaurant name? Once we take in what the user says, we use that as the feedback back into our algorithm. So this is what our test data was. Since we didn't already have existing labels for all the words that were in the corpus, we took the top 1,000 most popular search queries and manually label them. So the top 1,000 queries were, like, we thought this made sense because the top 1,000 queries were about 45% of the total search traffic. So, like, we have a manual label, we have a predicted label. So over here we can see that for burger, the manual label was a restaurant because a lot of people, because of the way the search works currently, people were searching for restaurant names. So that's why the person who was labeling it labeled as a restaurant. But our algorithm labeled it as a dish because the word burger was present in a lot more dishes than it was in restaurants. So this is what our results of the FastText classifier were. We had 88% true positives for each label across all labels, and a mean accuracy of 84% across the labels. So we talked about spell correction, and we talked about how we built an intent classifier. The next step is to talk about query expansion. So what is query expansion? The purpose of query expansion is to find what the user intended to look for rather than what the user typed into the search bar. So essentially, it broadens the scope of the query by introducing additional tokens. So these tokens, what we wanted them to be of two different types. One, synonyms, and the other, translations. So in the example that I have used before, coffee and cappuccino can be considered as two synonyms. And ayam is the Indonesian word for chicken. Because GoFood has the largest user base in Indonesia, we had a lot of Indonesian words in our corpus as well, which is why we thought having translations would be an important relationship to capture using semantics. So how did we actually go about doing this? We know that most computer algorithms cannot take in text-based data and they cannot analyze text-based data. So we had to find some form of numerical representation to represent this data, and we did that by building word vectors. So one way of building a word vector would be to just consider a one-hot encoded representation, but that would mean that every single word is completely independent of each other. That means there would be a completely different vector for coffee as compared to the vector for cappuccino. But this is not what we wanted. We wanted some way that would encode the semantic information within the vectors itself. So one way we found to do this was to build word embeddings. So word embeddings are essentially a encoded way where the vector is a much smaller vector compared to the size of the vocabulary, and the distance between vectors is somehow related to the semantic relationship between the vectors itself. So how do we measure how the vectors are actually related? We use this metric called cosine similarity, which essentially is a function of the angle between the two vectors. So say you have vectors like vector A is coffee and vector B is cappuccino. Then the angle between them, theta, would be very small because coffee and cappuccino are two very similar words. So cosine similarity takes up values between 0 and 1, and the higher the value, the closer to 1 the value is, the more similar the two words are. So here is an example of how the vector relationships can be captured. So let's look at this. Ayam goreng, so we know ayam means chicken, goreng is fried. So ayam goreng means fried chicken, and bebek goreng means fried duck. So the reason I've given these examples here is that because a lot of our data is in Indonesian, we need to make sure that the relationships that we capture also account for the words in both English as well as Indonesian. So say in this diagram, if we take ayam goreng and we subtract the vector for ayam, and then we add bebek to it. So we get the vector for bebek goreng. So the cool thing about word embeddings is that they also sort of, in some semantic way, follow the laws of vector algebra. So let's talk about how we actually went about training these embeddings, and what kind of data that we had. So the biggest challenge that we faced in this entire project was actually figuring out how we should structure our data so that the algorithm that is trying to learn these embeddings could capture the kind of semantic relationships that we wanted the similar words to have. So we had search-based data, and we had booking order data. So for a single context, we wanted to consider the search query that was used to place the order, the restaurant name from which the order was placed, and the names of the dishes that were ordered. So we did a lot of iterations to consider exactly how we should structure these data sets, and we found that the best way to structure this was by sort of this way. So if we have a single order, we take the query term and the brand term as a single context, so to say, and the query word and each of the cart items sequentially for like the same context. So the reason we did this was because of the base assumption that when, say, a user types in coffee, they go to Starbucks and they order a cappuccino. So we want the algorithm to learn that there is a relationship between coffee and Starbucks, as well as coffee and cappuccino. So that is why we structured our data like this. And to train our embeddings, we used a Python library called Gensim, and the API that we used was the word-to-vec algorithm. So essentially, this is what the API sort of looks like. We wanted the vector size to be 50, and the minimum count of the words in our corpus had to be 50 for us to, for the Gensim to actually consider the word vectors. So this is a TSNE plot. TSNE is a dimensionality reduction technique which takes the word vectors, dumps it down into 2 dimensions, and sort of visually displays it. So we can see that, so this is for a subset of the data we have, and since most of the words in our corpus were in Indonesian, a lot of these words are in Indonesian as well. So we can see this cluster over here at the top, which has been blown up, that we saw that all of these words are actually different types of fish that are very popular in Indonesia, which means that all of the fish actually had word vectors that were very close to each other, which had a very small cosine similarity with respect to each other. Then another cluster that we found down over here is a cluster of different types of noodles that are very popular in Indonesia. So all of these, again, had vectors that were very similar to each other. So how do we use these word vectors for query expansion? We take, for each search query that we have, we find the word that has an embedding that is closest to the embedding for the search query, which means that the embedding for the search query and the embedding for that for the expansion term have a very high cosine similarity. So let's look at some examples of the words that we observed. Over here, we have 2 different types of noodles that are very common in Indonesia. These, if the search query was one, the expansion term was the other. So this was the kind of relationship that we wanted to establish. The other is chicken and duck. This kind of relationship we saw because a lot of Indonesian dishes use chicken and duck interchangeably. The third relationship that we found was juice and juice, which is the Indonesian word for juice. So this took into account the kind of translation relationships that we wanted to capture. And the last one was a little bit of a surprise for us. We saw that the word vectors for McDonald's and Burger King were very similar to each other. So yeah, this is not what we were expecting, but was like a happy consequence. So we looked at spell correction. We looked at how we built an intent classifier. and how we found the query expansion terms for the search query. Now let's look at how we build all of take into account all of these outputs and insert them into the search query for Elasticsearch. So I mentioned that the probability of the search query corresponding to each label was taken into account in the search query. So the way we take it into account is by using it as a boost value. So the boost value for each of these intents sort of makes sure that if there is a match with that, so if there is a restaurant that okay, so for example, if someone searches for Korean, and we say that the probability of Korean being a cuisine is very high. So that means that all restaurants which have the cuisine Korean will get boosted up and have an additional weight compared to restaurants that don't have the cuisine Korean. So that is how the output of the intent classifier is taken into account. Now let's look at how the output of the query expansion is taken into account. So we have all the expansion terms from query expansion based on whatever was most similar to the search query. We add these as additional match clauses for the restaurant name and the dish names in the restaurant. And the boost for these is a function of the corresponding cosine similarities between the expansion terms as well as the search query. So here is an example of the match clause for the matching with the restaurant name. So over here we can see that we've used the fuzziness auto, which means that even if the person typed in, say, going back to our example of crispy with a K, and they were looking for crispy creme, that means it would still match with crispy with a K even if the query had been corrected to crispy with a C. Over here, then, so say if the search query was I am and the expansion term was chicken. So we have two of both of these inside a dismax clause. So the dismax clause exists because we want to make sure that if there is a search result which has both of these terms, it is not given a higher importance than if a search result had only one of these terms. And this, the values after the caret refer to the boost values. So the boost value over here will be a function of the intent class being a restaurant, and the boost value over here will be a function of the cosine similarity between chicken and I am, as well as the intent being a restaurant. So this is very similar, the match with the menu items or the dish names within that restaurant. And this clause is very similar to what the restaurant name matching clause was, except that the boost values will be a function of, instead of the intent probability being a restaurant, it will be a function of the intent probability of it being a dish. Then we have the boost clause for cuisine. So for 3 would be a function of if I am was a cuisine, and the reason we have only one match clause is that because we want to boost all results where the cuisine matches I am. So how do we bring it all together? We join all of these 3 components that we saw in the previous slides into one should clause. That means if there is a restaurant that matches even one of these clauses, it will be retrieved from the entire list of restaurants in the nearby radius of the user. So now let's talk about how we surface results. Say this person typed in I am into the search bar. We can see this would be how the search results would be displayed. This is a list of restaurants. So the first restaurant we can see has the word I am, which is the search query, in the name itself. The second restaurant has chicken in the name, which was the expansion term for I am. The second, third, and fourth restaurants have a cuisine called chicken and duck, which means that the cuisine matched whatever the search query was, and these results were boosted up. Now the last result that is on the screen, there is no obvious match with I am or chicken in these search results. That means that the obvious conclusion is that this restaurant contained dishes which matched with the search query. So how do we test this? We use an A/B testing method where we direct a certain percentage of our search traffic to the experiment that we're running and measure the search to booking conversion lift over that. So we saw a search to booking conversion lift of 30%, which was pretty awesome. So yeah. So now let me sort of conclude by talking about some of the related efforts that we're working on. We're also working on building a food knowledge graph, which is essentially an ontology of all the dishes and restaurants that we have in our corpus, in our database. And the other features that we're working on are auto-suggest and autocomplete for GoFood search. So yeah, that's it. Let's look at what the key takeaways from this talk were. I talked about why a simple text match may not be enough for search. And in this section, I explained why it is important to be able to understand the query and how to why surfacing relevant results can actually improve user experience. Then I talked about what are the key components of query understanding. I explained how we use a spell corrector, an intent classifier, and query expansion, and how we collate the outputs from all of these into a query semantics engine. So yeah, that's it. Thank you. If you guys have any questions, I'd be happy to take them. Yes.
No questions?
Hello.
Yes.
So I have a question you have the idea of boosting whenever you're showing a search result.
Yes.
So I'm asking like if some restaurants, do you uh, go to reach to restaurant telling that if you want to get a boost, then you should show this, or is it how business know that you are boosting results based on the queries? Is
So
there
the
any
way,
relation?
sorry, could you, the last part I didn't hear you.
So I'm asking, is there a recommendation system where you say to restaurant if you put these details then you can get more boost? Just
So that would be the way a business value would contribute, like, so how the business would contribute to the boost values. But the way that our algorithm works over here is only taking into account what the search query is and what the intent of the search query is. This bit does not take into account any kind of business metrics or some whatever, like partner boosts or whatever. Yeah. Any other questions? Yes.
I don't know if this was covered in the intent part, but I was wondering, we also know a lot of information about the users, right? I mean, what did they search in the past? Who are they? What is their age group and so on, which could be used to understand or interpret their queries better than, doing it generically.
Yeah. So when right now, we take into account all the historical searches across users to figure out what the intent is. Because if there is a user who does not have any past data, then would be difficult to, build like an intent classifier or use query expansion for that user. So we just take into account all the past searches which have been for, say, a specific search query, use that to expand the query and figure out what the common intent has been in the past.
Okay.
Oh, so you have a question? Yeah. Mike?
Hi.
Hi.
So can this engine understand queries like, the cheapest restaurant or the best restaurant, like additional intents?
At the moment, no. At the moment, we're only considering 3 intents, but that is something that we will be working on in future iterations.
Great.
So there's one question that somebody's raising.
Hi.
Hi.
Yeah, just wanted to know about the embeddings part. We learned similar words, right? How did you validate that the embeddings are correct and the similar embedding words are actually the words which are similar?
So everything through experimentation. We ran experiments with different versions of embeddings, and we tried to measure what was the lift in performance for that set of embeddings, and if there was a lift, if there was not a lift, that is how we kind of validated the model, because user behavior is the only indicator of how the embeddings are performing. So for example, if we had that ayam and chicken example, when we did that, we saw like a significant lift and boost for that type of embeddings. But if we had something like, say, chicken and beef, that saw a drop because a lot of people who eat chicken don't eat beef. So yeah.
Yeah, hi.
Hi.
This is an add-on for the first question. So, how do you calculate that boosting? Is there any parameters that has to be considered for the boosting?
So you mean the function of it being the
Yeah,
intent
how is it
probability?
boosted? Yeah, how do you get that
Um,
boosting list?
So essentially, the boost values are a function that we have derived. It's not like a static value, but yeah, like I can't exactly like tell you what that function is. So if you want, we can talk about this in more detail after the talk. So yeah.
Hey, I was wondering if the search results that you show, is there a way you can validate what you're showing is relevant statistically and not only through A/B testing?
Right now, no. Like our main agenda is to improve, say, search to booking conversions. So whatever helps us achieve that is what, according to us, is the best way forward. So yeah.
Hi. So this question is regarding like the cleaning of the text. So in that, what if like generally what happens is that people miss spaces while typing things. So two words might occur like without a space, which are like legitimate words, or in fact like one word might be misspelled and joined with like without having a space, like with another word. So do you do any pre-processing to correct that?
Yeah, so our spell correction algorithm kind of takes that into account. So say you have a word, crispy chicken, which is without a space and spelled with a K. This is the kind of example that you're talking about, right? Yeah. So what it does is we kind of iterate through all the words that are within an edit distance of 2. And for all the edits, we consider inserts, deletes, transposes, and replaces. So yeah, so this would mean that the K can be replaced with a C, and a space can be inserted between the words. So the bigram crispy chicken would have a higher frequency than probably any of the other edits that can exist, which means that this particular word would get corrected to crispy chicken with a C. Yeah. There's one question
Is it a
here.
question? Because we have 1 minute left. Okay. Okay, this is the last question for this session.
Okay.
How often is the whole computation of the embeddings done, and what is this change in latency you observed from before and after?
The computation's done like every day at midnight. We have a pipeline that runs, and sorry, what was the second? Change in latency. So the outputs of the embeddings, like all the similar terms, we put them in a Redis on the same server. So essentially, there's not a very significant change in latency because Redis is pretty fast. Yeah. If there are any other questions, we can take them offline after the talk.
Yeah.
So yeah. Thank you.
So round of applause for